Hi, this week we'll talk about some high-K material and some FinFETs. As we've learned before, we should increase the epsilon to get a good current. And so to that we should increase the epsilon, and so we use some high K material, high K gate or high K material. To use some high K material, we should consider these things. For like the high dynamic constant level, and some high barrier heights, and some interface in the interface quality, and the interface cap or the interface trap, something like that, and some thermodynamic stability, and some fixed oxide charge, and some capability of the gate or in the process. So we've learned about the barrier heights and the dielectric constant. Uh, as the dielectric constant means decay, so it should be higher or higher. So we shut down some uh, PATIO3 or something like that. And then we've learned about the interface stats, that which means, as you can see in this picture, um, as the band gap goes like this, and this means there are some charges in it. That means we have some cap. We can see the charge as a cap. So as the band gap looks like this, there are some caps inside here. It means there are some interfaces traps. Uh, so like we can see like this, and to but we have some caps and we have some interfaces trap, but so we use some interfaces layers like SiO2, or silicon nitride or something like that, to get some to reduce some of those bad issues. Yeah, and if we had some interfacial layer, we have some tunneling, but it is more less than we use as just a high K layer, not including some interfaces layer. Uh, so to interface this is the engineerings that we use at the interface. There are lower interfaces, and we set some gate dielectric, and then we've pour some upper interface, and then the gate electrons. uh, gate electrode, yeah, something like that. And then we've talked about the thermodynamic stability, which is very important, because as the process goes by, we should consider some thermodynamics, because as the gate doesn't melt at some point, or the other things will melt, and that means the device will crush off. And then we've talked about some metal gates, and something like this. So as we learned something like this, we talked about the zircon oxide, and the hafnium oxide is the best high K material. High K material. And then we've learned about the FinFETs. Uh, as we can see in here, the FinFET is we as the FinFET band gaps seems like this. We seems very good in here. And there are some gate all around nanowire or something like that. I've learned that too. And why we should use FinFET is because we can get a better control in the channel with the gate. Because as we can see in this picture, you might think the width gets lower, but as this is a 3D, as so we looked at as a cross-section view, we can see that the width, we have some width, but the total width includes the heights of the gate. So the total width will grow, and if you look like this, we can control the channel by upper and the sideways and the low and the bottom waves. So we can control them as a four-way. That means we can control the channel more easily. But making a FinFET is very hard, and we should use some ALD process to grow some fins. Grow some fins, yes. And we installed some hafnium oxide, and as and and the FinFET had some good subthreshold swings, because as you can see in here, the if we do not consider some CIT, then you can see the COX by CB. But when there is a FinFET, when there's FinFET, and so there are some when there are depletion region as a fully depleted, when they are fully depleted because it is FinFET, it seems there are no Q moving, because Q moving at the voltage gate, because they are already fully charged. So we can see that the Cox by CB comes 0. It means the N will go more closer to the number 1, and that means the subthreshold voltage will go to directly to the Boltzmann tail. So we can see that FinFET has a very good subthreshold swing. Thank you.